Today, think of me as your master technician because we're going to walk through an absolute masterclass on diagnosing and repairing starter solenoid contact failures. We're getting right down to the nuts and bolts of what happens when a vehicle just flat out refuses to start. So grab your notepad, pull up a stool, and listen closely. Let's dive right in.
Here's our lesson plan for today. We're covering the dreaded starting click, the physics of contact failure, the master diagnostic guide, teardown and repair secrets, and finally, prevention and material upgrades. We've got a lot of ground to cover.
Okay, part 1. The dreaded starting click, also known as the rookie mistake. Picture this, right? A customer rolls into the shop, you turn the key and click. Just one loud click, but the engine absolutely refuses to crank. You check the battery voltage, and hey, it looks fine. Now, the absolute rookie mistake here is to instantly blame the battery, or worse, just condemn the entire super expensive starter assembly and chuck it in the scrap bin. But listen, that single click, it's actually telling us something crucial. It tells us the electromagnetoid coil inside the solenoid is doing its job. The real problem is the current just isn't making it to the motor.
So here's a real-world veteran trick for you. If you take a wrench or even a hammer handle and give the solenoid housing a solid tap while someone else turns the key and it suddenly fires right up, well, you've just proved the motor itself is perfectly fine. Why does that work? It's simple. That physical impact just shifts the internal plunger a tiny fraction of a millimeter. It's just enough to let those worn internal contacts touch at a slightly different, maybe cleaner spot. It literally confirms you've got contact surface damage, not a dead starter motor.
Moving on to part 2, the physics of contact failure. We're going inside the high voltage cauldron.
To fix this right, you really got to understand the terrifying physics happening inside that little housing. See, the starter solenoid isn't just some basic switch. It actually serves two massive simultaneous functions. First, it acts as a heavy-duty electrical relay connecting the battery straight to the starter motor. And second, it mechanically slams the pinion gear right into the engine's flywheel. This little component is a high-stress bridge, carrying anywhere from 150 to over 400 amps of current every single time you turn that key. It's intense.
And that brings us to what's really going on in there. Think of a welder striking an arc. Seriously, it's the exact same idea. When that internal contact disc gets close to the contact posts, an electrical arc actually forms in the microscopic gap before they even physically touch each other. This arc reaches temperatures well over 3,000 degrees Celsius right at that localized spot. Guys, that is way hotter than the melting point of copper. Literally every single start is a violent micro-welding and erosion event. So knowing that, it makes sense how this brutal environment destroys those internal contacts over tens of thousands of starts. It basically happens in 3 phases. Phase 1 is arc erosion. This is where ionized copper vapor is literally blasted away, leaving these microscopic craters behind. Then phase 2 kicks in, mechanical wear. The everyday vibrations from the running engine cause fretting. And finally, phase 3 is thermal cycling fatigue. You know, blasting from ambient temperature straight up to searing heat and back down again. That causes the copper surface to harden, develop microcracks, and just steadily drive that internal electrical resistance right through the roof. Now let's look a bit closer at the physics of the copper itself. We use electrolytic copper because its thermal conductivity is amazing at dissipating all that intense arc heat. But there is a major catch when it comes to copper's electrical resistivity. If those contacts heat up to around 150 degrees Celsius during a start, their electrical resistance actually jumps by a whopping 49%. Combine that with its high thermal expansion, causing massive thermal shock stress, well, it completely explains that dreaded hot start failure. You know the one, where a vehicle starts up perfectly in the morning, but leaves you completely stranded after a long drive when everything is totally heat-soaked.
All right, on to part 3, the Master Diagnostic Guide featuring the gold standard of testing.
In this shop, we do not guess, we test. And here is the gold standard method for proving exactly what's failing. Grab your digital multimeter. You're going to connect the positive lead directly to the battery's positive post. Remember, the actual post, not the clamp. Then put your negative lead right on the solenoid's battery terminal. Have your buddy crank the engine and read the voltage. After that, move your negative lead over to the motor terminal on the solenoid and repeat the process. What we're actually doing here is a highly targeted voltage drop test right across those internal contacts while they're under load.
Keep this chart handy because it is literally your diagnostic Bible. If you measure anywhere between 0.0 and 0.2 volts of drop across the contacts while cranking, you're golden. They're in great shape.
But if you start seeing 0.2 to 0.5, or even up to 1.0 volts, you've got significant wear and they need replacing soon. Now, anything above 1 whole volt, those contacts are completely fried. They are literally eating up your voltage before it can even reach the starter motor.
Let's apply this to a real-world scenario so you can easily tell the difference between a bad battery and a bad solenoid. Pay close attention to this. A dead battery is going to cause the voltage to collapse across your entire system the second you put it under load. But solenoid failure? Totally different beast. Bad contacts act exactly like a clogged dam. The battery voltage itself stays perfectly high, but a massive voltage drop happens right across those worn contacts, completely starving the starter motor of the power it's begging for.
And hey, we cannot forget about the coils that are actually driving all this action. Inside, you've got a pull-in coil, usually sitting around 0.8 to 2.5 ohms, and its job is to slam those contacts closed. Then you have a hold-in coil at 3 to 6 ohms that keeps them squeezed together. Now, if that pull-in coil's resistance drifts out of spec, it loses its magnetic force. That means it closes the copper contacts way too slowly. And guess what? A slower closure drastically increases the duration of that 3,000-degree arc we talked about earlier. It will literally destroy a brand new set of contacts in a matter of weeks.
Furthermore, because the starter motor is desperately trying to compensate for that massive voltage drop caused by those bad contacts, it pulls heavily on the current. If you slap a clamp meter on there, you'll see the current draw surging all over the place. Instead of a nice, steady, normal draw of maybe 140 amps, the starter is now pulling well over 300 amps just trying to turn the engine over. It's just a nasty, vicious cycle of electrical strain.
Okay, part 4, teardown and repair secrets. Let's look at the veteran's trick. This is where we get to save the day, because 9 times out of 10, you do not need to replace the entire starter assembly. Here is your teardown checklist. You really only need the basics: a 10mm wrench, a 12mm wrench, and your trusty multimeter. Once you pop that housing open and clean out the internals, you want to do a thorough visual inspection. You are looking for craters or pitting deeper than 2 millimeters on the contact disc. Look for heavy black carbon buildup, and definitely inspect the interior walls of the housing for copper splash marks. Yeah, that's literal splatter from those micro-welting explosions we talked about.
All right, here is the veteran's secret to really saving your customers some cash. On a lot of starters, like your typical Denso or Bosch units, that heavy copper disc inside is actually perfectly symmetrical. So, if it still measures over 4 millimeters thick, but one side is heavily pitted, you just pull it out, flip it 180 degrees to expose the fresh copper face, pop in a new contact spring, which by the way is absolutely crucial for maintaining the right pressure, and button it all back up. Boom! You've just fully restored the solenoid's conductivity for literally pennies.
Finally, part 5, prevention and material upgrades. We're playing the long game now. Now that you've got it fixed, let's talk about how to make sure this repair outlasts the rest of the car. Standard electrolytic copper contacts are totally fine for standard vehicles. They usually last about 30,000 to 50,000 start cycles. But if you're dealing with modern start-stop vehicles, the ones that restart the engine at every single red light, you absolutely need an upgrade. By switching over to silver copper or silver tungsten composites, you drastically reduce the electrical resistance, and you can cut that arc erosion by up to 70%. That pushes the lifespan well past 100,000 cycles.
Look, as a master tech, half your job is actually educating the customer. Teach them these daily habits to stop early wear in its tracks. Tell them to keep those battery terminals pristine, maybe apply a little dielectric grease to the post threads, and always keep the battery fully charged. A low battery just causes low voltage, which exponentially intensifies those destructive arcs inside the solenoid. Warn them against those rapid-fire click-click-click start attempts. That just overheats the contacts instantly. And most importantly, if the engine takes a long time to crank because of some fuel or spark issue, they need to fix that immediately. Extended cranks will absolutely roast those solenoid contacts.
All right, the starter solenoid contact is arguably the hardest working electrical interface in your entire car. So, armed with all this knowledge about the crazy physics happening inside that little cylinder, the next time you hear that single click, what kind of mechanic are you going to be? Are you going to guess, pull out the parts cannon and throw a brand new starter at it? Or are you going to grab your meter, test the voltage drop, open that housing up, and fix the real problem?